when you decide to change lecture, inform me through Patrizia. If you not inform me through Patrizia, I assume that lecture starts very well. Okay. Any questions regarding previous lecture? Did you try to solve this little problem? So what did you get? What's the power of density for Fermi energy? Okay, today's lecture will be devoted to Fermi liquid. And Quasiparticles. So in your course of solid state physics, did you calculate specific heat for Fermi gas? Maybe. So what is in solid state and statistical phase? Okay, let's repeat a little bit what you know about ideal Fermi gas. So, as we discussed it last time, fermions are subject to Pauli principle, which forbids two identical particles to be characterized by the same set of quantum numbers. So at least one quantum number should be different. This is a subject of Pauli principle. Therefore, when we construct a ground state of non-interacting fermions in three-dimensional case, for example, we need to fill in all states for the momentum smaller than Fermi momentum. So these states are filled, and states with a momentum larger compared to Fermi momentums are empty. So this is how Fermi sphere occurs. And I said not yet interaction, no interaction yet is taken into account. Then we found a connection between Fermi momentum or corresponding Fermi energy, which is defined as Pf squared over 2m, and total number of particles in the system. For example, it was found that for three-dimensional case, Pf was equal to 3 pi squared n over v to the power 1/3. Once again, from now on, I will put h equal to 1. Well, for two-dimensional case, if you solve it at home correctly, Pf was equal to 2 pi 2 pi n over v, something like that, right? And the distribution function for fermions at zero temperature is step-like. So this is n is a function of energy, here energy, here is Fermi energy, and this is 1, and this is 0. So this is how distribution function looks like, and we said that at finite temperature we have a smearing of this distribution function which occurs in the stripe of the width of the temperature. And as we discussed, typical Fermi energy in metals, and we are dealing, of course, with the free electrons, and you know that free electrons is a specific property of bulk metals. You need something to conduct current, and this is why metals are good conductors. So typical Fermi energy is of the order of 1 to 10 electron volts, which is 10 to the 4 to 10 to the 5 kelvins, and we see that at room temperatures, which we are now, the approximation of zero temperature is quite good, because the temperature is much smaller compared to Fermi energy in normal metals, which we are going to deal with. Okay, so now maybe I write down the Fermi distribution function just to repeat it for you. It's 1 over e to the power e minus mu over temperature plus 1, and Fermi energy, as I said, is the chemical potential at zero temperature. As any thermodynamic chemical potential depends on temperature. We will discuss it next week. I will check with Professor Müller how he derived the specific heat, and see whether we need to come through main step of this derivation once again, or it's enough to switch to magnetism, which magnetism of free electrons, which I would probably do. Yeah. Okay. So this is a ground state. This is a ground state which tells us that all states, all quantum states characterized by the momentum below Fermi surface are filled and above Fermi surface are empty. And now we construct the excitation. How should we construct the excitations in the system? Well, it's quite clear. We just take one state below Fermi surface, remove a particle from there, and put it outside Fermi surface. So this is a way to create excitation in a system. Clearly, the energy of this state is higher compared to energy of the ground state, because ground state is characterized by minimal energy. And from now on, we call the excitations of quasiparticles below Fermi surface as holes. It's holes. And for excitations above Fermi surface, we can give different names. Sometimes people say it's a particle, then hole is antiparticle. Sometimes people say it's an electron. Let me give two names, particle or electron. Don't confuse it with the real electron as elementary particle. This is kind of jargon existing in the literature, so you don't need to think about quasi-particle electron equivalent to elementary particle electron. It's not the case. As I said, quasi-particle is synonym of excitation. And in this particular case, when we discuss ideal Fermi gas, and we are still discussing ideal Fermi gas, the particle, the excitation which lives above Fermi surface is electron, while the particle which lives below Fermi surface is Hall. Why did I say that it's not elementary particle? It's not equivalent to elementary particle electron. Because, well, for the case of ideal Fermi gas, we can of course say it is, because the mass of this quasi-particle is identical to mass of electron. There is nothing which can change this mass. However, in real systems, the gas of the real metal is not an ideal gas. Therefore, there are effects of interaction. Your electrons in the environment, your particles in the environment talk to each other, and as a result, the real mass or the real band structure lead to significant deviation from bare mass of electrons. For some metals, this value of the mass is close to mass of elementary particle, but for some systems, for example, systems known as heavy fermion, this mass can be dramatically different from the bare mass of elementary particle. Electron dramatically means even 1,000 times more heavy than this bare mass. Why? We discussed in our course. However, it's not always that effects of interaction leads to the fact that mass becomes heavy and heavy. It can be the other way around. In semiconductors, for example, typical gallium arsenide structures, the mass is lighter. And from the course of band structure from the solid state physics, you know that for tight binding model, when you discuss electrons hopping from side I to side J with a hopping matrix element Tij, and then your energy EP is something like minus 2 times T cosine PA. For simplicity, I take one-dimensional case. If you expanded the cosine, it will be minus 2T plus T A squared P squared, right? And this constant can be incorporated in a chemical potential. It's just shift where the origin where you calculate your energy, and this one, Ta square, can be identified as 1/2 mass. Therefore, mass is 1/2 times Ta square. So you see that the mass in band, it's actually characteristic of a hopping matrix element between sides I and J. So this mass, in principle, has nothing to do with the mass of elementary particle. Elementary particle is defined in vacuum. Our electrons live in the crystalline lattice and subject to periodic boundary conditions. So you see that the mass of excitation is not necessarily coinciding with the mass of free electrons. Okay, let me give you a brief reminder what energy is, if you didn't discuss its in thermodynamics. Once again, using this distribution function, we can calculate total number of particles in the system, which is the way we establish connection between Fermi momentum and density of particles. So it's 2 times V integral over d3p over 2 pi cube m pi, and energy is equal to 2 times v, and I remind you that factor 2 comes from summation over spin. It's integral over d 3p over 2 pi cube pi squared over 2m and p. So if we calculate the energy of the ground state, and let's do this simple calculation at 0 temperature. Now I put temperature equal to 0 and continue here. It's 2 times v, 1 over 2m, and here integration over a solid angle gives us 4 pi. We have 8 pi cube here, and the remaining integral is the integral over inner side of the sphere, so ball, and what remains here, it's p squared from Jacobian times p squared from here and dp. So this integral is, of course, Fermi momentum to the 5th power over 5. So what do we have now is, let's collect here, it's like that. So it's 1 over 5 pi squared, right? We write v, and this is pf5 over 2m. Of course, we can write it as pf cube, pf squared over 2m times pf cube. And this is a Fermi energy. Then energy per unit volume, E over V, is equal to 1 over 5 pi squared times Fermi energy. And from here, we have Fermi momentum cube is equal to 3 pi squared n over v.
In the second line, what do you mean by NP?
Sorry?
In the second line, NP. No, in the integral.
NP is this one. NP is n epsilon p, and here is epsilon t, where epsilon t is p squared over 2m. So we can write that energy per particle, okay, is equal to 3/5 of Fermi energy. This is kind of equation of state. Well, of course, energy per unit volume is proportional to the Fermi momentum to the power 5, so it will be proportional to 5/3 power of the density. So this is how this equation of state looks like. Okay, let's now come to excitations, and as I said, we remove particle from the Fermi sphere and put it outside, and of course it costs energy, and it costs as much energy as we need to go deeply inside Fermi surface. So it makes sense to count the energy of excitations from the Fermi surface. So just let me define psi p, which would be energy of the excitation, and in order to do it, I have to subtract from kinetic energy the Fermi energy, right? And I can write it down as 1 over 2m here modulus P minus Pf times modulus P plus P. Of course, it's very costly to remove particle from the area close to the centrum of Fermi sphere, because for that reason you pay price of the Fermi energy. And as I said, Fermi energy is electron volt is 10,000 Kelvin. Therefore, what temperature can do and what is effect of smearing is just affecting very narrow shell of the order of temperature, which will let electrons go outside and holes be created here. Therefore, I can say that my momentum P is approximately Pf. Therefore, I can write that the energy of excitation is equal to, approximately equal, Pf over m, and here P minus P. This is nothing but velocity, and we call it Fermi velocity. So the energy of excitation is equal to Fermi velocity times modulus P minus P. So if we plot it, we get linear dependence of the energy as a function of the momentum. You can ask me how come it happened that we started with the free electrons characterized by quadratic dispersion law and arrived at Fermi energy. To keep in mind the picture, just understand what we did. So this is parabola. This is our P squared over M. What we did here, we zoomed in this piece of the spectrum, subtracting Fermi energy, and this is a picture. Of course, close to energy which separates field states and empty states, the spectrum can be linearized, and as I said, for realistic temperatures, when we don't melt our piece of metal, we are fine to characterize our excitations with this dispersion relation. One of the objectives of my lectures is to teach you how to read literature. So therefore, I would like to give you different examples what people usually refer in papers. So when you read papers about Fermi systems, you will definitely find that people are referring to that situation, but sometimes in literature, people count energy differently for electrons and holes. So this branch is for particles. It is positive. But sometimes people characterize holes. So this is particles. Sometimes for holes, another definition is adopted, so we know the sign. So this is Pf squared over 2m minus P squared over 2m. And therefore, this branch is reflected with respect to this. So sometimes people plot this as a dispersion of excitation, and when you will discuss superconductivity, you will see that what's happening in superconducting state when two electrons can attract each other in the vicinity of Fermi surface, then there is a gap opening here. So don't
please don't see any contradiction between what I have said you initially and what you will get in the lecture of superconductivity. Everything is very consistent, and the reason why people count the energy of the holes that way is related to redefinition of your operator, secondary quantized operator. I hope you're familiar with second quantization. I don't need to repeat you what it is, because after 2-3 lectures, when I finish with the general stuffs, we come to analysis of Hamiltonian, and we'll be deeply using second quantization and formalism in our calculations, trying to diagonalize many particle Hamiltonian. So what I'm saying is the creation operator of the electron is C, but defining the hole, one can introduce a new operator B, which tells us that to create an electron means to destroy a hole, or other way around, B dagger is C, which says that to create a hole, one needs to destroy an electron. And since in diagonalized Hamiltonian, the Hamiltonian can be written as sum over P epsilon P Cp dagger Cp, then we can write it as a sum over positive P epsilon particle P C dagger P Cp minus sum over P smaller than Pf epsilon particles. Now I introduce B dagger B, because minus comes from anti-commutation, and then I see that energy of holes is equal to minus energy of particles. Okay. So we repeated that, and now let me come to interacting picture. So what would be a hypothesis and what would be a guess about a situation when the interaction is taken into account? In the time I'm cleaning the board, if you have any questions, please ask me. Again, I would appreciate if you tell me that if what I am discussing now is well known to you and you don't need it. Because I presume, well, I have quite long experience to work with students teaching in France and Germany for many years, and my experience says that it is never a bad idea to repeat things. First of all, people present it differently. Second, people present different aspects of the same thing, sometimes using different language, different notations, and so on and so forth. And repetition is never a bad idea. Okay. So, question, what happens with interaction? And the guess and the hypothesis is that the spectrum of interacting electrons is equivalent to the spectrum of non-interacting electrons. So we may still write is psi pi is equal to Bf modulus pi minus Bf. However, as I have already mentioned, the Fermi velocity is Bf over m star, where m star encodes the presence of interaction, but it is not all in order to complete picture, I need also to say something about Fermi moment. And the hypothesis says that the Fermi momentum is connected with the density of particles in the system the same way as it is for ideal Fermi gas. It's quite not intuitive to understand this. This is the essence of Landau theorem, which can be generalized for the case of field bands and conduction band. I'm not going to prove this theorem. In order to do it, I need to involve myself in quite cumbersome calculation. I just formulate you the hypothesis which exists on the level of theorem, proven theorem. Therefore, it's a statement, and it says that system of interacting electrons is, at the end of the day, equivalent to system of non-interacting electrons, while the mass is not the mass of the electrons, and Fermi momentum is the same way connected with the total density to the power 1. Okay, it's a very powerful statement. It means that in order to understand, in order to construct theory of normal metals, what we need to do, we need to study theory of Fermi gas and see what can we learn from this theory. Good, but this is not all the truth. Of course, these excitations talk to each other, and therefore there is decay rate which is appearing in the system, which characterizes as the process of decay of the quasiparticle. And the next question, which is very reasonable to address, is in which case these quasiparticles, which I have defined, are well defined. So let me formulate it as when quasiparticles well defined and in order to answer this question, we need actually to compare two things. Which things? Let's think about wave function, many-body wave function of a system. The fact that quasiparticles freely propagate in the system means that the wave package which we constructed moves through the system without changing the form. It would be the case if quasiparticles don't know anything about each other. However, they do know, and therefore there is a damping which characterizes the process which happen with the wave package when it propagates. So in order to have quasiparticles as well-defined objects, we need to be sure that this damping or decay of quasiparticles is much smaller compared to the energy of the quasiparticles. So we need to see that gamma p is much smaller than psi p, and we already know what psi p is. And if and only if this is the case, we are fine to say that the objects we have defined that way are good objects and can be used for descriptions of the system. If this condition is not fulfilled, bad luck, we need to do something else. So, The question now is, what is gamma p? How to calculate this gamma p, and how to check this condition. And this is what we are going to do in the next 10-15 minutes. Have you ever discussed the quasiparticles in Fermi liquid? I think no. Yeah? Good. Okay, I'm going to present very simple calculations which do not involve any heavy machinery of many particle physics, which comes later. I mean, I don't know to what extent we will be able to touch upon some advanced methods, but the nice thing about theoretical physics is that many things can be explained and visualized in terms of very simple arguments. Okay, good. The question is formulated, and let's start giving answer on the question. In order to do it, again, I will not specify any particular shape of the. I will use very general arguments based on the probabilities. However, the estimate will hold. So now I'm redrawing this Fermi energy, and in order to let two quasiparticles talk, I will now plot two of them for some shape, for some particular choice of parameters. So I assume that there was quasiparticle 1 which interacts. There is electron 1 which interacts with some state 2 inside Fermi surface. So then this electron inside Fermi surface goes out, creates a hole. So, and as a result, initial states are 1 and 2, and final states are 1' and 2'. Once again, the electron, namely the excitation, interacts with some state inside Fermi surface such a way that this state becomes empty, so there is a hole formed here, and the electron goes out. Of course, we have conservation of momentum and conservation of energy, which means that the momentum P1 plus P2, sum of the momentums in the initial state, is equal to P1 prime plus P2 prime. I will denote this quantity as P capital. And of course, energy is conserved. So energy 1 plus energy 2 is equal to energy 1' plus energy 2'. So let's look at this particle. Fix particle 1. So the probability which characterizes this rate WP is proportional to the integral over all intermediate, over all states. So dp1 prime, dp2, dp2 prime, and here I have to put delta function which says us about conservation, epsilon 1 plus epsilon 2 minus epsilon 1 prime minus epsilon 2 prime. This is the conservation of energy, and then delta function which characterizes conservation of momentum. And this is a function of P1, which is the only external parameter. We come to this equation for the rate when we discuss kinetic equation, but what I said now is quite transparent. And this is a gamma, which we are doing. Gamma P1. So I'm looking for some excitation, some quasi-particle existing above Fermi surface. I see how it talks to some particular states inside Fermi surface such a way that this process of scattering is taken into account. Of course, I can write many configurations when this quasi-particle talks with another quasi-particle, when states, well, if it talks with some state inside Fermi surface, there is only one option. It can go out because all states are filled, and this particle cannot scatter such a way that the state 2 changes to another state inside of Fermi surface. The same for n prime. It cannot be inside of Fermi surface. It can only be outside Fermi surface because states in are filled. So this is why this is the process which I take into account, and in zero temperature I believe that there are no any other holes inside of Fermi surface in order to be filled in the process of scattering. Okay, let me now plot the momentum conservation. So if we have P1 and P2, this is P, and at the same time it is equal to P1 prime plus P2. Okay. To calculate, to take the integration over one of the momentums is very easy. Let's integrate out momentum 2. So then we drop this delta function and write it as integral over dp1 prime dp2, and here it's a delta function of epsilon 1 plus epsilon 2 minus epsilon 1 prime minus epsilon 2 prime, where epsilon 2 prime is expressed in terms of this conserved momentum. So we substituted P2 prime from this equality to this one. So therefore, there are only two variables which remain. Integration over vectors P1 prime and P2 prime assumes integration over modulus of this vector and angle. But we can argue that integration over angle removes remaining delta function. Why it is so? Because, as I said, epsilon 2 prime is equal to P2 prime squared over 2m. It's equal to P minus P1 prime squared over 2m, and angle between P1 prime and P is actually fixed by the conservation law of the momentums. Therefore, when we integrate out the angle, we remove the delta function. And what remains is integration over dp1 prime dp2 modulus. And as I said, the quasi-particle which I'm looking for is living in the very vicinity of the Fermi surface. So then, the only thing I need to do is to put accurately the limits of integration and estimate this integral. Let's do it. If you don't understand anything, if you don't understand logics, because I'm not doing the calculations as mathematicians are supposed to do. I'm not proving the theorem. I'm teaching you how to do very simple hand-waving estimation. But it assumes some logics which I follow, and you need to be used to this logic somehow, otherwise you are lost. And of course, please think about it, please read the book. These arguments which I am giving to you now are well described in Abrikosov's book, Fundamentals of Metal Theory. So if you are lost with my explanation, please have a look in the book and please try to repeat these arguments. So what I'm saying now and what I will do now is to write down some chains of inequalities to bound P1 and P2 and then calculate simple integral. Very simple integral. So let's now do this chain of logics. So P1 is approximately Pf. By the way, let me put something here, which is plotted on the figure, but not yet written. So I assume that P1 is bigger than Pf. P1 prime is bigger than Pf. P2 is smaller than Pf. And P2 prime is bigger than Pf. This is what is drawn in the picture. This characterizes me initial and final state, which I take into account. But now I'm going to say that all momentums P1, P2, P1 prime, and P2 prime are living in the vicinity of Fermi momentum.
I do not understand how you have an excitation above the Fermi surface.
What do you understand?
I don't understand how you have excitation because there is a particle 1 excited.
The logic is like that. I took some extra electron existing above Fermi surface, some excitations which is above, and I will follow it because this is my external parameter. So then I'm saying how this extra electron can interact with my Fermi sphere. For example, it can interact with some state inside Fermi sphere such a way that after the interaction, the state 1 scatters to state 1 prime, and this is the only possibility for it, because it cannot scatter inside the Fermi sphere. All states are filled in. There is no room. Pauli principle works. However, the same is applied to the state 2. It cannot scatter anywhere inside Fermi sphere, because all states are filled in, so it can only scatter outside Fermi sphere. And there are no other particle living above Fermi sphere. So this is the only process, actually, which I need to take into account. And then I will integrate over all possible final states, namely states 1 prime, 2 prime, and all possible positions of a particle 2. It can interact with this one, it can interact with this one, it can interact with this one. So I'm integrating out all possible state, and if I do it, I will find how the decay rate depends on the momentum. This is what I plan to do. But as I said, I should not go deeply inside Fermi surface. It's too costly. So what I need to take into account is the fact that this quasi-particles is deliberately chosen to live in the vicinity. This was my condition. I implemented. But all the other states, 2, 2 prime, and 1 prime, then fixed by this condition. They all should live in the vicinity of Fermi surface, otherwise I pay enormous energy. Okay, then from the condition that now P1 plus P2 is equal to P1 prime plus P2 prime, you see I removed vectors from this because energy is linear and conservation of the momentums being in the vicinity of Fermi circles means the conservation of the modulus of the momentum. If I subtract, let me express P1 prime, since I need to do integration over P1 prime and P2 prime. P2. So I need to write some inequalities for P1 prime and P2. From this, P1 prime is equal to P1 plus P2 minus P2 prime. If I subtract Fermi momentum from this equality, it will be P1 prime minus Pf is equal to, let me write it this way, P1 minus Pf plus P2 minus Pf. So I subtracted Fermi momentum twice, then I need to add Pf minus P2 prime. This is still equality, right? But P2 prime is larger than Fermi momentum, right? So this is then smaller. So this guy is negative. P1 minus Pf plus P2 minus Pf. So one inequality I need, P1 prime minus Pf. I hope you understand how equality becomes inequality since this condition is implemented. On the other hand, P1 prime is larger than Pf from here. P2 prime is larger than Pf, then this is P1 plus P2 minus P. This is the same as this one. You don't need to be afraid of this inequality. Therefore, I would like to write something about P2. Having in mind these two inequalities, I write that P2 is larger than 2Pf minus P1. Or, and smaller than Pf, right? Then P2 is larger, P2 minus Pf is larger than Pf minus P1 and smaller than 0. Okay? So this is all what I need. Let's remember this is what we are calculating. So, gamma P1 is equal to integral over dP2 integral over dP1 prime. Let me subtract Fermi momentum from both of them. So this is the same as integral over dP2 minus Pf integral over dP1 prime minus Pf. So this is just for the sake of this one. Of course, it is positive. So let me call it P2 tilde, and this is P1 prime tilde. So now I put the limits of integration. The integral over P2 minus Pf, so d P2 tilde, is taken from Pf minus P1, and you remember that P1 is my argument which fixes the moment of move 1, and integral over dP1 tilde, this is 1 tilde, is taken from 0 to P1 minus Pf minus P2 tilde. You see that this is P2 tilde, and that's it. Now I'm fine to calculate this integral. It's not a big deal. Pf minus P1, 0 to P2 tilde. Here I have P1 minus Pf minus P2 tilde. So, continuing the line, the first term doesn't depend on P2 tilde, so I take this on the limits 0 and Pf minus P1. It is equal to P1 minus Pf squared minus P2 tilde square half in the limits Pf minus P1, 0. Sorry, it's of course plus here. It is plus here. So what I got at the end of the day, it is P1 minus Pf square half. This is the answer. Let's look at this answer. And compare it with Xi. So Xi P1 is equal to V1 P1 minus Pf. Gamma P1 is proportional to P1 minus Pf square. So I can write down that gamma P1, if I now put all dimension constant, is alpha Xi P1 square over Fermi energy, where alpha is a constant of the order of 1, which I need to write down at the very beginning when I define the probability. What you see from here, that the condition gamma P is smaller than Xi P is equivalent to condition alpha Xi P square over Fermi momentum is much smaller than Xi P, or Xi P over Fermi energy is much smaller than 1. What does it say? It says that the quasi-particles are well defined as long as